Here's the example. A free charge of 1 coulomb is placed at a vector position 1, 0, 0 meter. A free charge of minus 3 coulombs at 1, 1, 1, and a free charge of 5 coulombs at 3, 3, 0 meter. What is the flux of D through the surface of a sphere centered at the origin if its radius is 0.5 meter? Okay, so this is testing you about the enclosed surface and what is enclosed and what is not enclosed. The first one, okay, so I'll draw out the scenario. This is my Z. So I got one charge here, 1 coulombs. This is at x1, 0, 0. And then I have one charge at somewhere here. This is minus 3 coulombs. And then I have 3, 3, x, 3, y3. Which is 5 coulombs. And then the first one, if I have a sphere of 0.5 meter centered at the origins, what is the flux of D? So basically asking about flux of D, the electric flux through the surface of this sphere. Gauss' law tells us this is equals to, what is this equals to? So what's Gauss' law? The flux of D is equals to total free charge enclosed within the surface. Okay, so if I have a surface with a radius of 0.5 meter centered, okay, 0.5, let me use a different color so that okay, so 0.5 is here. So if I have a sphere, it probably looks something like this. Okay, so any of the charge is actually enclosed inside this sphere. If this sphere is of 0.5 meter radius. This charge here, this is 1 meter away from the origin. This charge, you have 1, 1, 1. So the distance from the origin will be 1 squared plus 1 squared plus 1 squared. There will be square root 3. Obviously, that is bigger than 0.5 meter. And that is also not inside my sphere. This is obviously not inside my sphere. So what's the electric flux? So this is, I hear someone say something, 0. Everyone agree? Why is it 0? So no charge inside that sphere because the sphere is tiny. Okay, all the charge is outside. So according to Gauss' law, this is equals to sum up all the charge inside that sphere. But in this case here, none of the charge is inside this tiny little sphere because the radius is only 0.5 meter. How about the second one? 2 meter. What is the electric flux equals to? If it's 2 meter, how many charge enclosed? Which charge are enclosed? 1 coulombs and the minus 3 coulombs. So in total, what is that equals to? -2. The third one? 5 meter. This distance here, there will be 3 squared plus 3 squared square root 18 squared, that is smaller than 5. So all 3 charge will be all enclosed, yeah? So if I draw a sphere of 5 meter in radius, then all the charge will be enclosed. And what is this equals to? Okay, so there will be 1 plus minus 3 plus 5. Okay, so there will be 3 coulombs. You get the idea what coulombs or what Gauss is saying. What Gauss law talking about? So he's talking about enclosed inside that surface. So it's very important, it's inside the surface of the enclosed surface. So in the first one, nothing is inside the enclosed surface, then the electric flux is equals to 0. Second case, you have 2 charge, one of 1 coulombs, the other one of minus 3 coulombs. So the total charge enclosed is minus 2 coulombs. And the third one, you have 3 different charges enclosed, and therefore you have 3 coulombs. The electric flux is equals to 3 coulombs. So we work that out. So what is the net flux of D flow through the surface of the cube that enclose all the charge? If it's a cube. So just now we're talking about the spheres. So now if we have a cube, a large cube, enclosed also, isn't it? Cube is also an enclosed surface. So if we sum up all the different sides of the cube, it's also an enclosed surface. So what's the electric flux of that? Zero? Or what? Any idea? It says specifically it encloses all the charge, all the charges. And we're still talking about the flux of D. We're still talking about phi E. What's that equals to? Any idea? 0? 3? I heard 3. Everyone agrees 3? So someone says 3 coulombs. Why? Because it says so, isn't it? It said all the charge is inside this cube. And that's what Gale said. Gale said that the enclosed surface, so all the charge enclosed in the enclosed surface. So in this case here, it's also 3 coulombs that is enclosed inside that cube. And therefore, it is still 3 coulombs. So it's the same as 5 meter. 5 meter also has a 3 charge enclosed. Even if I draw a large cube, also have the 3 charge enclosed. And that also equals to 3 coulombs. Okay. So that is testing your understanding about what Gauss is saying. So as long as the charge is inside the closed surface that you draw, the electric flux will be equal to the sum of all the charge inside it. Doesn't matter what surface you draw. Okay, you can draw a bubble, you can draw a cube, draw a cylinder. As long as the charge inside, the electric flux will be equal to the total sum of charge inside that surface that you draw. Okay, so that is just basically the solutions of what I have just talked about just now. So it's true for any closed surface of any shape, provided that it's fully enclosed the charge. So it doesn't matter it's a cube, cylinder, as long as it's enclosed and the charge is inside it, and the electric flux will be equal to the sum of all the charge inside that surface. The flux is unaffected by the nature of the materials contained within the closed surface, only by the amount of free charge enclosed. Doesn't matter whether you have dielectric inside. So this cube or the sphere that we introduced, it doesn't matter whether it's a dielectric materials or is it free space or is it a conductor. As long as the charge is inside, then the electric flux will be equal to the total sum of charge, because we're talking about free charge. The free charge enclosed. So we apply Gauss' law to find D produced by the distribution of the charge by first drawing an enclosed or closed surface around the charge known as Gaussian surface. The surface that we draw is called Gaussian surface, and then we apply the equations of d dot ds equals to q, and that's our equations. So we draw a surface around the charge, and then we work out this integral, and that has to be equal to the charge enclosed inside that surface. So if I have a point charge, I draw a sphere around that charge, and d dot ds, if I integral over the whole of this surface, and that has to be equal to the charge enclosed inside that surface. The difference between drawing a sphere and a cube is the difficulty of the integration. Okay? So if I draw a sphere around a point charge, then it will be a very simple integration, because the electric flux density on the surface of the sphere are constant. So at every point on the sphere, D is constant. If I draw a cube, then D is not constant. That at different points on the cube surface, D is not the same. and therefore I have to solve this integral every single point on the surface of the cube, and that is very difficult to solve. But if it's constant, we can take d out of the integral, and then we're just solving a surface area integration rather than solving a dot product integration. You get the difference? Let me try illustrate this a little bit more. And that leads to how you choose okay, if I have a point charge Q, if I draw a Gaussian surface, which is a sphere. So earlier on, when we studied Coulomb's law, we know that E is equals to Q over 4 pi epsilon naught R squared. That is what we have learned earlier on. So in this case here, R, on this surface here, every point on this surface, R is the same. Okay? If I go around my sphere, R is the same. So this value, Q, 4 pi is a constant, epsilon naught is a constant, R is also constant. So at every point here, my electric field is the same. That is what we learned in topic 2 on electric field. In this case here, my electric flux, so my Gauss law, we know that this dot product, these two vectors is in the same directions. The electric field always perpendicular. This is my ds, and therefore this is the integral. And then because we know d is constant, I can take this constant out from my integral. I'm just doing this integration. And this integration is well known. We know that this is equal to 4 pi r squared. And then we know that this is equal to charge enclosed inside. But if I draw a cube, on this surface here compared to this surface here, they are all a different distance from my cube. Although we know that this is still equals to Q, but this integration now is very difficult because I need to do my ds is this, my d is this, and then I have an angle here. And then for this, I also have my ds here, and then my d is of a different direction. Again, I have a different angle. This dot product is very difficult because at every point of the surface, d is pointing a different direction to the surface vector, and therefore you have to solve that dot product. And therefore, and you also need to, they're also of a different distance from the point. And therefore, these integrations become very difficult to solve. Whereas in this case here, d is constant, so you can simply take d out of the integration because it's just a constant. Okay, it's just like if I try to integrate 3x dx, 3 is constant, I can take 3 out of my integration. I just do this, right? But if this is not constant, this is a function of x, then I cannot simply take my function out from the integration and just integrate x. I have to solve my function x with the x. and it become more difficult to solve. Okay. So the point I'm trying to get is that you have to choose a Gaussian surface that gives you constant electric flux density around that surface. So for a point charge, it will be a sphere that will be constant, so that you can make the integration simpler. And you don't choose a cube because that integration is very difficult to solve. Although both electric flux is equals to Q, this is what we established just now in the example, but solving this integral is different between a sphere and a cube. Only a small number of cases where this procedure is simple, and these are the one that we are going to consider in this module. That's the one that we have a good simple integration that we can do rather than using cube over a point charge. That will be a very difficult integration to do. The Gaussian surface is not real, it's just a mathematical construct for you to solve this Gauss law. Neither have to represent a physical surface, so you can just draw any mathematical surface over your point of interest. You don't have to represent any physical surface.